Hi everyone, I'm Alex Rojas and welcome back to my YouTube channel. So today's video is about how physicists determine the age of the Earth. The motivation of why I'm doing this video is because I'm extremely surprised of seeing on YouTube or TV debates about what is the real age of the Earth. And this number, the age of the Earth, is being settled for over 5 decades. So this is not any groundbreaking or new cutting-edge physics. This is 1950, 1960s physics, where they got this number. Actually, the number that they got back in those days is with a very similar precision to the one that is the current value. And it is a 4.54 billion years, now 6,000 years old, with only 1% uncertainty. So let's say you want to show or try to convince someone that the evidence are clear, and well, you want to explain how this is done. Well, you will need the following ingredients. One of the first ingredients that you need in order to determine the age of the Earth is a primordial meteorite. So what is a primordial meteorite? It's a rock. It's a piece of rock, basically. And what is primordial about it is that this rock or this meteorite was formed during the formation of the solar system. Therefore, the multi-elemental composition, that means the iron to lead to nickel to silicon ratio inside the meteorite, resembles the same ratio that was present during the formation of the solar system. Therefore, if you extract a grain inside from the center of this meteorite, and you do you study with analytical chemistry, you study what's the composition of that grain, you will somehow be probing what is the composition of the primordial solar system. So this is one thing that you will be that you require. The other one is another sample, another rock, but from the primordial Earth. That means that when the Earth was still forming, and there is a very good sample that is from the moon. Now, why the moon? Well, what happened on Earth is that Earth is very active. We have a lot of volcanoes, tectonic plates moving, we have pollution, atmosphere. The moon is very quiet, except the surface where it's exposed to solar winds and radioactivity. The rocks inside in the moon are there is not much change, and also there are a lot of evidence as well that the moon is in fact a piece of Earth. When the Earth was forming, there was a collision between a big comet or meteorite or another planet, and from that collision a chunk of the Earth, which is now the moon, came out, was expelled, and then it ended up rotating around our planet. Therefore, talking about the moon or any sample from the moon is in principle any sample, Earth sample. So that's another rock that you will need. And the third ingredient that you will need is an isotopic ratio technique. Isotopic, I will explain what isotopic means, but basically you need to measure the specific ratio or the concentration of different isotopes inside each of these rocks. In this case, you will be studying the isotopic ratio of lead, and I'll explain why lead is very important. So these are the three ingredients, and once you have all these three ingredients, you can start doing the measurement in order to calculate the age of the Earth. Perfect. Now we have all the ingredients needed to determine the age of the Earth, but we still need to go over some physical concepts that would allow us to know how this number was obtained. And one of the most important concepts is the concept of isotope. So what is an isotope? Well, let's assume you have an atom, and this is the classical or the usual picture of an atom, which is a central nucleus surrounded by a cloud of electrons. And let's also assume that this atom is neutral, so no missing or extra electrons in the cloud. Well, we know that the electrons are negatively charged, so the cloud itself has a net negative charge. But if this atom is neutral, you must have some positive charge in the nucleus that will balance that negatively charged cloud. And what gives the positive charge to the nucleus are some particles known as protons. The protons, they have the exact same numerical value for the electrical charge, but the opposite sign. That means that the electrical charge of a proton is the same as the electron, but the electron is negative, the proton is positive. That's basically it. Now, if you have, let's say, 6 protons inside the nucleus, that will determine what is the element that you're talking about. That actually is the atomic number. The number of protons inside the nucleus is the atomic number and is the location of the place inside the periodic table. So let's say if you have 6 protons, that will be the carbon atom. There is no other element with the same that could be identified as a carbon atom with any other proton or number of protons inside the nucleus. For example, if you add an extra proton, instead of 6 you have now 7, that will be a complete different element, that is nitrogen. So the atomic number is what dictates what's the atom itself. Now, that's basically all you need to create an atom. But if you look closer inside the nucleus, you will realize, and by looking closer I mean with a particle accelerator, that is the nuclear physics microscope, you will realize that it's not only protons inside the nucleus, you will have another particles, and these particles are called neutrons. Now, the neutrons, they have no charge, otherwise they will break this balance made by electrons and protons. So they are neutral, but they have very similar mass than the proton, and actually it's a bit higher than the mass of the proton, and their job basically is to, what happens is that when you put all these protons inside the nucleus, because they have the same positive charge, they repel each other and they want to fly apart, and these neutrons serve as buffers, and they keep them somehow, they add extra or nuclear force to keep them together. Anyways, but you can, the character or the identity of the atom is independent of the number of neutrons. You can have 10 neutrons or 5 neutrons or 7 neutrons, and if you have, as far as you have 6 protons, it will be carbon, and it will behave exactly like a carbon atom, and you won't be able to tell from chemical reactions. Well, so for example, let's assume you have, in the case of carbon, you have 6 protons, you know, that's the only way you can have carbon, and you have also 6 neutrons. That will make a specific type of carbon known as carbon-12. Let's assume another example. You have the same 6 protons, but instead of 6 neutrons, you will have 8 neutrons. If you have 8 neutrons, that won't be, still is carbon because it has 6 protons, but it won't be the exact same carbon. It will be carbon-14. So there you have it. It's the same element, but with 2 different masses. This is the nucleus will weigh 12 units of mass, and this will weigh 14 units of mass. That is the concept of isotope. Isotope is nucleus with the exact same chemical characteristics because it has the same number of protons, but with different masses, and the masses is related to how many neutrons you will have. Okay, another important concept that we need to understand is radioactivity and half-life. Going back to the previous example, we have 2 isotopes, carbon-12 and carbon-14. And the difference between those two is only the number of neutrons, because actually the number of protons is what gives the identity of this element, equals to carbon, was identical. So you have 6 protons for the carbon-12 and 6 protons for the carbon-14. But in the case of the isotope of carbon-12, you have only 6 neutrons, and in the case of carbon-14, you have 8 neutrons. So these two behave identically or chemically the same. Actually, you must have some carbon-14, some of this isotope inside your body, and some of this isotope inside your body, the carbon-12 one. Now, what is radioactivity? Radioactivity is the mechanism that a nucleus has to get rid of an excess of energy. It can be by getting rid of extra mass, or getting rid of just by emitting electromagnetic radiation, or by breaking apart. So in the case of this example, these two nucleus, carbon-12 is pretty stable. It is a system that it is at the kind of a minimum of energy if it is at the ground state. But the carbon-14, because of an excess of neutrons, it has 2 extra neutrons, it is not as stable, and it will find, or it will try to find a way to go to a more stable system. And the way it does it is by converting one of the neutrons inside its nucleus into a proton. So it will make one neutron disappear. So now instead of 8, you will have 7 neutrons, and that neutron is made into a proton. So you will have an extra proton, and then you will have a new system with 7 protons and 7 neutrons. Well, if it has 7 protons, we know that this changed the atomic number. Therefore, this has to be a very different element. In this case, it's nitrogen. And 7 protons and 7 neutrons, it will be nitrogen 14. Now you may say, okay, but there is a problem right there, because you had only 6 units of electrical positive charge, which were by 6 protons, and now you have an extra one, and you're not conserving electrical charge. Well, what happened also is that while this decay was happening, the nucleus emits an electron and an antineutrino. So, but that's a different story. And this is what balanced or fulfill the conservation of charge. The important thing is that this decay, or this is what we call as radioactivity, is a way or a path that a nuclear system has to get rid of an excess of energy and go to a more stable or a lower energy system. Now, another important property of radioactivity is the concept of half-life. If you have a sample that contains a certain amount of carbon-14, let's say, and you wait long enough to see what happened or how many of them disappear, that means that at some t equals 0, you have a certain amount of carbon-14. Let's assume you have 100. And then you wait long enough until you have a ratio of 50 and 50. Let's say 50, half of them disappear. Now you have only 50 carbon-14. And because you know that each isotope of carbon-14 must be converted into nitrogen-14, so when you measure this ratio between these two elements, this ratio will be equals to 1. So you have the same, you started with a ratio equals to 0, so no nitrogen-14 and 100 carbon-14 now is the exact same amount for both. So the isotopic ratio later in time that you're measuring now is different than or the original one. You will find that the time that you have to wait until this happen is approximately 5,300 years. So you have to wait 5,300 years every time in order to have a sample that half of the amount of carbon-14 disappear. And that is the concept of half-life. So this will be exactly just like the half-life. This is this 5,300 years that you have to wait until half of the carbon-14 in your sample disappear is the half-life of carbon-14. And that by itself gives you a hint on how, by measuring the isotopic ratio, that means the ratio between different isotopes in a sample, give you an idea, and also if one of the members of the sample is radioactive, give you an idea of how long you have to wait or how long time passed before the original sample and then your measurement. Alright, now you have all the ingredients needed plus the physics that you need to determine the age of the Earth. So how do you do that? Well, you grab either a moon rock or a primordial meteorite and you will measure the isotopic ratio of the isotopes of lead. Now, why lead? Well, first of all, lead comes in 4 different, let's call them flavors, or 4 different stable isotopes, which are lead-204, lead-206, lead-207, and lead-208. Now this, once you have these isotopes of lead, they won't decay, they won't disappear, they will stay forever like this. Now, why lead? Why lead is so important? Well, lead comes from specifically these three isotopes. They come from a decay chain. They are the final result of a decay chain. In the case of lead-206, is from the decay of uranium-238. For lead-207 is uranium-235, the great-great-grandfather. And for the case of lead-208, by the way, lead-208, any samples of lead that you grab on Earth, about half of that lead, it is this particular isotope. It's the most abundant one, is thorium-232. Now, that doesn't mean, I'm not trying to imply that uranium or thorium decays directly to lead. There is a decay chain. There's a lot of alpha particles emitted and electrons and some energy released. Now, these decays are particularly important because the half-life of these decays are comparable somehow with the age of the Earth. For example, this decay chain, for every nucleus of uranium-238, in order to be converted, well, not half of them, to be converted into lead-206, you have to wait 4.47 gigayears. You see this large number. The half-life of uranium-235 until you find some lead-207 is 0.704 gigayears. And for thorium-232 to make lead-208, you have to wait 14.1 gigayears. So these are the different half-lives. Now, if you okay, what about lead-204? Well, lead-204 is very peculiar. It doesn't come from any decay chain. Whatever amount of lead-204 was created during the creation of the solar system, or was present during the creation of the solar system, it will remain the same. So that's a kind of a constant that you will have. And so the idea is the following. You grab a primordial meteorite, this rock which is a primordial meteorite, and one of the key parts of a primordial meteorite, especially those made of iron, is that iron and lead, they combine chemically well. They can mix, they can blend very well. But iron and uranium or thorium, they don't. So when this small meteorite made mainly of iron was formed, you can have it can have this amount of lead, but it won't have any uranium. Therefore, it will preserve the ratio of lead-204 to lead-206 to lead-207 and lead-208 as the original or the primordial solar system during the creation of the solar system, and nothing extra was added to that ratio that you determine from the primordial meteorite, because it didn't have any uranium or thorium. Therefore, it remains, these values remain exactly, they preserve from the entire history, from the formation of this primordial meteorite to when you put it in the lab and do this measurement. Now, for the moon rock is different, because the moon rock comes from a larger object that contains a significant amount of uranium. And when you do this measurement, you find that the excess of lead-2 compares to the primordial meteorite, the excess of lead-206 or lead-207 and lead-208 compares to the primordial meteorite, gives you an idea how much uranium was transformed or converted into that specific lead. And by knowing that amount and by knowing the half-life, you will be able to determine how many years or how many gigayears passed since this rock was formed, and when you put it in the lab and do this measurement. So this is how scientists determine the age of the Earth, and this is how, by comparing these two samples and this isotopic ratio from the moon rock and the primordial meteorite, they arrive to this magic number. When I started to do this video, I was expecting that it would be very straightforward. I was surprised it is not. But I hope it gives you a very good idea how this is done and what are the ingredients and the techniques used to determine the age of the Earth. If you still have some more questions or you want me to go over some details that I'm probably not explaining very clear, please drop me a line and I will be happy to answer them. And thanks for watching. Bye.